is that of testing for the presence of jumps in data. And I'm going to sort of give you two sides of that problem, sort of 5A and 5B. And I'm going to start with 5B to provide some variety first, because I'm going to go now to a low frequency problem, and then I'll do 5A after that, which is sort of the high frequency approach to testing for the presence of jumps. There'll be sort of two very different methods. In fact, radically different, except for the fact that it's the same problem. They really have nothing in common in terms of the technology that I'm going to use for doing this. This is the wrong reference here, but it doesn't really matter. This is the paper for the other reference, but it's not important. This is a 2002 paper that's in the Journal of Finance. What I'm going to talk about here is try to test whether actually jumps are there or not, given that there is a Brownian motion. So conditionally upon the fact that you have a Brownian motion, the question is, do I need to have jumps in addition to that? So it's related to the previous question, but it's obviously not the same one. The previous question was given that we have jumps and a Brownian motion, how can we estimate the scale of the Brownian motion, or sigma, the volatility of the Brownian motion? Here, the question is, given that we have a Brownian motion, do we need to add jumps to the story? And in other words, if you only, and now the question is more complicated because we are only going to sample discretely, but we're only going to sample discretely at a finite frequency. So we are not going to allow ourselves to have high frequency data. So which, if you sort of kind of think about sort of the intuition that I talked about earlier this morning, it's probably more difficult to distinguish these things at that level. And one of the things I'm going to be doing is I'm going to be sort of thinking about alternative sources of data for sort of addressing that question, and at sort of low frequency. And in fact, I'm going to be using options to some degree to sort of see whether there is jumps as viewed from sort of the risk-neutral distributions of options. Now, so the object that I'm going to think about, which is sort of different from the objects we've talked about so far, is the natural summary object for the data at low frequency, and that's the transition function of the process. So these processes are all going to be Markov. So, you know, we're going to have Markov processes all the way through those lectures. And what you're looking at is you're looking at time homogeneous Markov processes. So you're looking at basically a process that goes from, you're asking, you know, if I go from state X to state Y, what's the probability of doing that in time delta? And that's that conditional probability density, P of delta Y given X, is what will be that conditional density or transition function for the process. And what I'm going to try to do is figure out a way of seeing if there are any features, and delta is not necessarily small here. Okay, I'm still using delta to think about sort of the same interval, but delta is not small. So delta could be 1 month, 5 months, 2 years, could be whatever is you know, the delta is separate from sort of the sampling at this point. Okay, so it's that particular object that we're looking at. Again, you've got a path, and you're asking what's the transition density of going from one state to the next. Okay, now, here's an example that shows you a direct, explicit answer to the question you're asking. The question you're asking is, you have some information about what happens at that discrete frequency. That may come from doing any sort of data descriptive analysis or something. So suppose that you have interest rate data, and that what you find is that your interest rate data, the conditional distribution of your interest rate data, so interest rate change, in a way that's normally distributed with a mean that is a constant plus another constant times the starting level, and a variance which is constant. It's not necessarily a greatly descriptive model for the data, but it's a possible thing. So you do some data analysis, and that's what you find. Well, if that's the case, then that's a discrete model that can be embedded into a continuous time model which is purely continuous. In the sense that, suppose you write down now a Norstein-Uhlenbeck diffusion, which is the continuous time diffusion that's in the middle, with a speed of mean reversion beta, a level to which you mean revert of alpha, and a volatility sigma, then you ask yourself in reverse, what's the conditional density at time interval delta that corresponds to this model? And it's well known that the answer is Gaussian, with a conditional mean that happens to be affine in R sub t, and a conditional variance that is independent of R sub t. It's just a constant with respect to R sub t. So, you've got three parameters. You can clearly match the conditional distribution that you found in the data to the conditional distribution that would be implied by this model. And the conclusion you get from that simple exercise is that if you are convinced that the data is indeed normally distributed with gamma 0, gamma 1, and delta 0, you can't reject the fact that it's possible that a purely continuous model would have given rise to the data you have. So if that's the empirical evidence you have, then you can't reject that the model was that diffusion. I mean, there's no way for you to tell me that that continuous time model is wrong if the data you have told you what's in the top equation. Now, so you just set those parameters and you're in business. Now, unfortunately, that's a calculation you cannot do in most cases. So that's an example, but that's pretty much one of the few examples for which you can do that calculation. So in general, you can't hope to answer that question. You can't hope to answer that question by sort of replicating that example to more general situations. I mean, you can. There are a few other examples, but that's about it. So what we're going to think about instead is thinking about, in the same spirit, sort of just like here, I'm sort of restricting P. I'm sort of figuring out what are the restrictions on P that would tell me something about the continuity of the sample paths. I'm going to try to think about ways where I can, even though I can't explicitly tell you what was the diffusion, perhaps there is something in that transition density that is explicit enough that I can run that analysis, find whatever I find for the distribution of the data at the discrete frequency, so find whatever I find for that equation, and then figure out whether that conditional density that I got from the data came or did not possibly come from a diffusive model, i.e. a model without jumps. And that requires that we think about the geometric implications of the continuity of the sample path. And for that, let's just take the same probability space, but take two different processes which have, let's call them R and R tilde, which have the same distribution, except that they are initialized at different points. So the first one is initialized at x, the other one is initialized at x tilde, and x is less than x tilde. And let's think about what continuity means. Continuity means that if at this time they are at those two levels, so say, US interest rates are 2%, ECB interest rates are 3%. Okay? If interest rates move continuously, then, and in a year, US interest rates are 3% and ECB interest rates are 2%, i.e. they've switched order. If I know where I am now and I know where I am in a year, and the process is continuous, then this can only happen if the paths have crossed. That's a geometric consequence of having continuous paths, is that you cannot reverse order without crossing paths. If you jump, then it's possible for you to reverse order without crossing paths. So for example, if interest rates move by the ECB deciding to lower interest rates by 100 basis points, then there's no crossing, but bingo, you actually have your reverse order. So in other words, if you have continuity, the paths look like this, and if one starts below the other, they will end below the other if they haven't crossed. But if they cross, it's possible, if they jump, it's possible to cross, to change order without crossing, if the jump just happens to be as in that picture. Now, on the other hand, if they are continuous, then you have the following simple consequence. Let's say at time t they are in the order I've described, x is less than x tilde. And let's say at time t plus delta, they happen to be in reverse order. If they are continuous, that means they've crossed. Now, that means there's a crossing point C. Formally, you can define the first Markov time at which the crossing happens. And then what happens after that point? Well, if the data generating process for those two processes is identical, and they are Markov processes, once they have crossed, meaning once you have reset them at the same state level, going forward, they become indistinguishable. The reason being that once you know they are at time tau, once they are at that stopping time, you recondition on their values at that stopping time, and once they are there, going forward, you cannot tell which one was which. So in other words, you have no way of preventing me from taking the path that is in bold and making it light, and taking the other one and switching the color. They have the same distribution. You can't tell them apart. A simple consequence of this is that, and I'm skipping here, but it's done, I will show you sort of briefly later on how it follows. A simple consequence of this, which you obtain from calculating that crossing that probability after and switching the order, is that, really surprisingly enough, you will find that you have continuity of the path if and only if the transition function satisfies the following requirement, that the log transition function, the second cross partial derivative, is positive everywhere. It's really remarkably simple, and it's true for every delta. That's the key. The key, of course, is that it's not just true in the limit when delta goes to 0, but it's true for any time intervals, and of course it has to be true for every x and y. So all by itself, any violation of this anywhere would be enough to prevent you from saying that you have continuous sample paths. Now that, of course, is a testable hypothesis. That's a testable implication of the continuity of sample paths that you can test at low frequency if you wish. So I'm just going to give you sort of a brief sketch of the proof of the necessary part. That will be the only proof I will show, but it's such a neat, simple proof that I think it's sort of interesting to look at this. So let's consider two sets, y and y tilde, with every element in y less than every element in y tilde, and those are the forward state values for the process. And let's calculate the joint probability that r is in y, r tilde is in y tilde, and there exists a coincident state, S, between the two, given where we started. Right? So let's calculate that joint probability. From what we've just seen, that joint probability is the same if I interchange r and r tilde, because once there exists a coincident state, that joint probability is identical. Do you agree? That joint probability is identical if I switch the order of the two processes any time after the coincident state. Now, once you are looking at the second line in that equation, at this line in that equation, you realize that the notion of having a coincident state is redundant. because given that x was less than x tilde, now they have actually reversed order. But if the process is continuous, the only way they could have reverse order is if there exists such a coincident state, which means that this probability is equal to the same probability without the existence of a coincident state. Because it would be impossible to have that event happen conditionally upon the starting value without the coincident state. Meaning that the probability that this and there is no coincident state is 0. And since it's equal to the probability that there is a coincident state plus the probability that there is no coincident state, it's the same. So that probability is equal to that. Now, so that's the same picture we've looked at before. Now, by independence of R and R tilde, if I take those two processes to be independent, that joint probability without the existence of a coincident state is simply equal to the probability to the product of the probability, because I took two independent processes. And same thing if I reverse the order, it's equal to that, where of course this is the cumulative distribution function from that transition density. Now, therefore, the probability that R is in Y and R tilde is in Y tilde without having ever crossed is therefore the difference in those two probabilities. Now, since the difference in those two probabilities is itself a probability, that means that difference is always positive. It's very simple. It's a very simple argument. It's a very simple geometric argument that basically says that difference must be positive. Now, all you have to do to get to the expression I showed you a little earlier is take the limit where y is a little set around a value little y, and y tilde is a little set around a value little y tilde, and this ends up being like a convexity calculation. Then it becomes the same argument as why a convex function is such that the second derivative is positive, right? Sort of take a convex function. What's the definition of a convex function? Well, you take 2 points away from that point, and the spread is always positive, so you are always above the tangent. And you can, it's a simple exercise in analysis to convince yourself that this is the same as saying that the second derivative at that point is positive. So at that point, it becomes the same argument here. So you have this for the density, and by taking limits as y tilde going to y and x tilde going to x, you end up with that argument. The sufficiency part is more involved. The fact that this is sufficient to say that you have continuous is more involved, but certainly at least by now you should be convinced that this is necessary. That if you have continuity of the sample paths, then the density must satisfy this requirement, which, as I said, is a testable implication. So here's one example. Let's try to see what happens if you take a model which is an Oster-Uhlenbeck. That's that model above. This is the classical Oster-Uhlenbeck process, linear mean reversion in the drift, and the noise is driven by a Brownian motion, compared to a model which is almost the same, except that the paths are driven by a pure jump process, which is a Cauchy process, the same process I used as an example this morning. Okay, so a pure jump Levy process with Levy measure constant over x squared. All right? And now, why those two models? Those two models are nice because they have explicit transition functions. The Oster-Uhlenbeck, obviously you know what it is, and the second model you also know what it is, because the Cauchy process has a known density function. I showed you that density function yesterday. Now, the two transition functions are, the solid line is the Brownian motion, is the Oster-Uhlenbeck driven by a Brownian motion. The dashed line is the Oster-Uhlenbeck driven by a Cauchy process. And what you see, of course, is that the one that comes from the jump process has much fatter tails. Shouldn't be a surprise. That's the difference between tails that look like 1 over x squared and tails that look like exponential of minus x squared. You know, they look very different, obviously. And what you get is you get fat tails when you have jumps, and you don't get fat tails when you don't have jumps. The question is, what's the criterion function that I just showed you? This is the transition function. This is p. Now, of course, it's easy to calculate log of p, and then the partial derivative of log of p with respect to x and y, varying those two variables, and then you should see what you get. Now, d2x dx dy log of p, for a Brownian motion, that's a straight line. Why? Well, because what's log of p for a normal? It's basically log of e to the minus, basically y minus x squared. So it's minus y minus x squared. Well, you take the second cross partial derivative, that's a constant. Differentiate 1 minus x squared once with respect to y, once with respect to x, you get a constant. So that's a straight line, and it's a straight line that's positive. Okay? In this particular situation. Now, on the other hand, you take a Cauchy process, and what you end up with. So why is it positive? I see some people frowning. That's because you get minus 2 y minus x. Differentiate that with respect to x, you get plus 2. Okay? So that's what you're getting. So it's positive because it's y minus x, it's minus y minus x squared. For a Cauchy process, you do the same calculation. It's not constant, but it looks like this function. And clearly, there are some x's and y's where it's negative. So at that point, you see that you are violating the criterion, which is not surprising since, of course, you have a jump process. Since you have a jump process, you're going to violate that criterion function. So, in other words, whenever you have a density function that is somewhat explicit, meaning that you can calculate d2 dx dy, then you can tell whether that's a transition function that corresponds to a continuous process or a transition function that does not. Now, empirically, what I'm going to do is I'm going to take the density function, the risk-neutral density that is embedded in the prices of options. Now, those of you who are working in Wolfgang's chair of statistics here are intimately familiar with this. You've been working with those risk-neutral densities in many different ways. So the density function I'm going to use to implement that test is the density function that's embedded in the price of options. So, and the way I'm going to extract that is by using options data. So what is this? This is the implied volatility from SPX options. SPX means S&P 500 options. So these are just equity options on the S&P 500 index. So that's our DAX index. And so we have equity options. And what you have here is you have an implied volatility smile. The data points, the dots on this graph are the actual data quotes. And what you have as the solid line is the fitted smile. Okay? So it's really, there's relatively little noise in those data because every practitioner uses the same way of fitting the smile to the data, so markets are self-fulfilling in that. Everybody uses the same model, so then the market data reflect the same model, and then you use the same model, and then you reinforce in your belief that this is a good model for those data, and this continues going on. So that's the data as a function of moneyness. From this, you know, if you're familiar with this, that you can extract the density from figuring out what is the risk-neutral density that corresponds to those data. And what you have here as the solid line is the risk-neutral transition density. So these were, I believe, 3-month options. This is the 3-month transition densities that correspond to different strike levels from those options. And what you see is that, of course, there's a big left tail. So that's a pretty consistent pattern in those options. Right now, it's really, really steep. The implied volatility, this is not recent. This is data from a few years back. I told you that's a 2002 paper. So this is quite old data. But the smile is always there. Right now, the data, if you look at the data the past few days, implied volatilities are in the higher than 70%. Well, they briefly were higher than 70%. Whereas here, and that's the at-the-money implied volatility, mind you. Right here, the at-the-money implied volatility in those data is about 25%. And right now, you're looking at an implied volatility at the money that is 3 times that. Plus, you add a very steep smile. So if you're asking yourself, what is the implied volatility if I'm 20% out of the money for an out-of-the-money put? I don't know what the number is, but you probably expect to pay 90%, 100% implied vol for this. So clearly, it's expensive to buy insurance against those events right now. But the bottom line is, that's the smile you're getting, and because it's downward sloping this way, that generates skewness in the density. So you have, compared to a normal, or log normal, which is the curve you see here, with the dash. With the dashes, what you get is you're getting an implied state price density curve that is really, really steep, that is really skewed, okay, with a really big left tail. Then the question is this left tail big enough that it can only be explained by jumps, or is it compatible with a continuous model? And how do you answer that question? Well, this is your p function. You're just going to calculate d2 dx dy of log of p and see whether it's positive everywhere or not. Simple enough. And this is sort of the time series of at the money implied volatility for that year, which I believe was 2000 or 1999. I'm not quite sure which one it was. But what you get when you did that is you get a diffusion criterion. So what is that diffusion criterion? This is the minimum of d2 log dx dy log of p over different values of x and y within the range of quoted prices. Okay? So if the minimum is negative, then that's enough for you to reject that you have a continuous model. And the answer is you're pretty negative, basically. So you are sort of fairly consistently negative in this, which means that effectively, as you look at those implied volatility smile, those implied volatility smiles are simply not compatible with a continuous model. The only way you can justify paying such a high premium for those out-of-the-money options, is by including jumps. Is by effectively saying, allowing for the possibility of jumps. And that's sort of what you have here. And the data seem to be pretty clear in that regard, that they're really calling for jumps. Now, I want to point out one thing though, which is a limitation of this analysis. If you come back to the argument I made at the beginning about the coincidence probability and the crossing, which is what ultimately leads to all of this. That argument is inherently a univariate or one-dimensional argument. Because the argument I made was that if you start in this order, you're above when you're starting, then you can only finish in reverse order if you cross, right? Well, this is true in one dimension. This is not true in higher dimensions. Because in higher dimensions, let's suppose you go in this way in a straight line. I can go and start above you and finish below you by going this way, around you, and without ever crossing your path. Which means that I can't rule out that you had a multivariate process that gave rise to those option prices that was continuous. I can rule out that you did not have a univariate, I could rule out that you did not have a univariate continuous process, but I can't rule out a multivariate continuous process. So that's that. The second thing that you might ask is, well, using sort of the mathematical finance jargon, this is under Q, not P. So you might ask, well, does that mean that you know there must be jumps under Q? What does that tell you under P? In other words, under the equivalent martingale measure, because that density is the equivalent martingale measure, assuming, of course, markets are complete, so that I'm extracting a unique Q. I'm extracting a unique Q from this. Well, aha, but now, wait. If you remember Gerson's theorem, if you have absolute continuity of those measures, you cannot have absolute continuity of a measure with jump with a measure without jumps. So in other words, if there are jumps under Q, there must be jumps under P too. It's easy enough to say because otherwise there are possible increments of the process that are possible under Q, i.e. with a jump, that would be impossible under P. In other words, the null sets under P and Q would be different, which would violate absolute continuity. Okay? So that is not, so in other words, if you test for jumps under Q, you effectively test for jumps under P as well, to the extent that you find jumps under that. Okay, so that's sort of what you're getting. So this is, for example, what you do for the 3-month maturity, and you see that sort of as you get down to some levels, your diffusion criterion becomes negative. So that's why you're rejecting that. And if you look at the whole surface, both in terms of current starting value as well as strike prices, which are your X and Y, what you see is the white areas are the areas where the criterion is negative. So if you have any white in this picture, you reject continuity. So that's that. So the conclusion is that option prices really say that jumps are present. And it's important to remember the peso problem, which is that there's a lot more information under Q than under P in this particular instance. Because if this was done for year 2000 or 1999, I don't remember. But certainly those were very good years. Certainly 1999 was a very good year for the market. 2000 was not quite so good. But 1999 was a great year for the market, so there were no jumps. Under P, there are no jumps. So you look at the time series of the underlying asset, you see no jumps. That doesn't mean that you will see no jumps if you look at options data. And that's simply because options data would reflect a risk premium for the possibility of jumps, even if there are no jumps in the data. And in economics, that's what sort of we call the peso problem. After a currency that's pegged to another currency, but has substantially higher interest rates to reflect the possibility that it might get devalued, even though your time series might look like a straight line, because it's completely straight.